orbital companions, objects locked by gravity into synchronized dance with planets. For Earth, that's always meant one thing: the Moon, our singular natural satellite, the only substantial body gravitationally bound to our planet, constant, familiar, alone. Except now it isn't alone. Astronomers tracking near-Earth objects have confirmed something unexpected. A small body, designated 2025 PN7, is moving through space in almost perfect synchronization with Earth, not orbiting our planet like the Moon does, not flying past on a brief encounter like asteroids do, but co-orbiting the Sun in a configuration that keeps it near Earth for decades. This isn't a satellite. It's not gravitationally captured by Earth's pull. It follows its own independent orbit around the Sunday. But that orbit, through remarkable cosmic coincidence, matches Earth's orbit so closely that the two bodies remain companions, moving together through space in a gravitational relationship called quasi-satellite motion. NASA's orbital dynamics teams have run simulations tracking 2025 PN7's past and projecting its future. The models show this object has been loosely associated with Earth for years, possibly decades, before detection. And it will continue this relationship until approximately 2083, when orbital evolution will finally cause the paths to diverge. For the next half-century, Earth has what some are calling a second moon. That's not technically accurate. 2025 PN7 doesn't orbit Earth. It doesn't belong to us gravitationally, but it does share our journey around the Sun in ways that make it a temporary companion, a cosmic fellow traveler on a decades-long voyage through the inner solar system. This is rare. Natural quasi-satellites are unusual. Only a handful have ever been identified around Earth. Each one provides unique insights into orbital mechanics, gravitational dynamics, and how small bodies interact with planets. And now we have another one to study, another example of nature creating complex orbital relationships that seem almost designed but emerge purely from gravitational physics. 2025 PN7 was detected in late 2025 by automated survey telescopes designed to find and track near-Earth asteroids. These systems scan the sky methodically, imaging each region multiple times per night to detect objects that move against the background stars. When something moves, it's flagged for follow-up. Most detections are known asteroids on routine passages. Some are newly discovered space rocks on trajectories that bring them near Earth. A tiny fraction are artificial satellites or space debris. But occasionally, the surveys find something interesting, something that moves in ways worth investigating further. 2025 PN7 caught attention because its motion was unusual. Not the typical hyperbolic flyby of an asteroid making a single close approach, not the circular orbit of Earth-bound debris. Its trajectory showed characteristics suggesting it might be in resonance with Earth's orbit. That warranted immediate priority follow-up observations. Additional telescopes pointed at the object over subsequent nights. Each observation refined the orbital determination. Position measurements at multiple times allowed calculation of the complete orbit. And that orbit revealed the quasi-satellite nature. The object is small. Diameter estimates based on brightness and assumed reflectivity place it between 20 and 60 meters. That's substantially smaller than the Moon's 3,400 kilometer diameter. 2025 PN7 is more comparable to a small building or large boulder than to a planetary satellite. Despite its small size, it's bright enough to be detected and tracked from ground-based observatories. That's fortunate because understanding its orbit requires continued observation. Small asteroids on complex trajectories need regular position measurements to refine orbital models and predict future positions accurately. Subscribe now, because understanding how 2025 PN7 maintains this quasi-satellite relationship reveals beautiful dynamics that govern how small bodies interact with planets throughout the solar system. The term quasi-satellite describes a specific type of orbital configuration. To understand it requires understanding how objects orbit the Sun and how Earth's gravity influences nearby bodies. Everything in the solar system orbits the Sun following Kepler's laws. Planets, asteroids, comets all follow elliptical paths determined by the Sun's gravitational pull. Earth completes one orbit per year at roughly 150 million kilometers from the Sunday. Small bodies with orbits very similar to Earth's same semi-major axis, same orbital period, similar eccentricity will remain near Earth as both orbit the Sunday. But near is relative. Space is vast. Being in similar orbits doesn't mean being close in absolute distance. Quasi-satellite motion occurs when an object's orbit is so similar to Earth's that when viewed from Earth's perspective, the object appears to orbit our planet. It doesn't actually orbit Earth, it orbits the Sunday. But the synchronized motion creates the appearance of Earth-centered motion when you track the object from our perspective. Think of two cars on a circular racetrack. If they travel at nearly identical speeds, maintaining nearly constant separation, from one car's perspective, the other appears stationary or moving slowly, despite both traveling fast around the track. The relative motion is small, even though absolute motion is substantial. 20, 25, PN, 7, and Earth are those cars. Both orbit the Sun at similar speeds. From Earth's reference frame, the asteroid appears to loop around us in a complex pattern, even though it's actually following its own independent solar orbit. This configuration is dynamically stable for limited durations. Earth's gravity perturbs the asteroid's orbit slightly. Solar radiation pressure affects it. Gravitational influences from other planets contribute perturbations. Over decades, these accumulated perturbations will eventually change the asteroid's orbit enough that it no longer maintains quasi-satellite motion. But until that happens, the relationship persists. Understanding the detailed dynamics requires diving into orbital mechanics. 2025 PN7's orbit around the Sun has specific properties that create quasi-satellite motion when combined with Earth's gravity. The asteroid's semi-major axis, the average distance from the Sun, is very close to 1 astronomical unit. This matches Earth's semi-major axis, meaning their orbital periods are nearly identical. Both take approximately 1 year to complete an orbit. But the asteroid's orbit isn't perfectly circular. It has some eccentricity, meaning the distance from the Sun varies throughout the orbit. This causes the asteroid's orbital speed to vary. When closer to the Sun, it moves faster. When farther, it moves slower. This speed variation is key to quasi-satellite dynamics. The orbit is also slightly inclined relative to Earth's orbital plane. This inclination means the asteroid doesn't stay in the same plane as Earth, but oscillates above and below it. Combining these factors, nearly matched orbital period, modest eccentricity, slight inclination creates a situation where, from Earth's perspective, the asteroid traces a complex looping path. It appears to orbit Earth in a retrograde direction, though it's actually orbiting the Sun prograde like Earth does. The loops occur because of the changing relative positions and speeds. Sometimes the asteroid is slightly ahead of Earth in its orbit, sometimes behind, sometimes closer to the Sun, sometimes farther. These variations combine to create the apparent looping motion. Earth's gravity plays a role by perturbing the asteroid's orbit slightly. Without Earth's influence, the orbit would precess and drift. Earth's gravity helps maintain the quasi-satellite configuration for extended periods by continuously nudging the asteroid's orbit in ways that preserve the resonant relationship. But this influence isn't strong enough to capture the asteroid permanently. 2025 PN7 isn't gravitationally bound to Earth. It could escape if given a small velocity change. The relationship is temporary, lasting only as long as the dynamical conditions that create it persist. Comment below. Does it surprise you that Earth can have temporary companions like this without them being gravitationally captured? NASA's orbital simulations have tracked 2025 PN7 backward and forward in time to understand how long this quasi-satellite relationship lasts. The results show this isn't a brief encounter. The asteroid has likely been in this configuration for years or decades already and will remain so until approximately 2083. That's over 50 years of companionship from detection, half a century where Earth and this small asteroid travel together, maintaining their synchronized dance around the Sunday. Why 2083? That's when accumulated orbital perturbations shift the asteroid's orbit enough that quasi-satellite motion breaks down. The asteroid will transition to a different dynamical state. It might become a horseshoe orbit companion following a different type of synchronized path. It might escape Earth's dynamical influence entirely and become just another near-Earth asteroid on an independent orbit. Predicting exactly what happens requires detailed modeling of all gravitational influences. Earth, Moon, Venus, Mars, Jupiter, each contributes perturbations that slowly change the asteroid's orbit. Solar radiation pressure, though tiny, accumulates over decades. Even relativistic effects from the Sun's gravitational field contribute at the precision needed for long-term predictions. The uncertainty in these predictions increases with time. We can say with confidence that 2025 PN7 will remain a quasi-satellite for at least several more decades, but the exact year when the relationship ends depends on perturbations that are difficult to model precisely over such long timescales. After leaving quasi-satellite motion, the asteroid won't disappear. It remains a near-Earth object, periodically passing relatively close to Earth on its ongoing solar orbit. It might even return to quasi-satellite configuration in the future if orbital evolution brings it back into the right dynamical conditions. These relationships can be cyclical over very long timescales. Earth has had other quasi-satellites in the past. 2025 PN7 isn't the first, and it won't be the last. But they're rare enough that each one is noteworthy. The most famous is 2016 HO3, discovered in 2016 by Pan-STARRS. This asteroid has been in quasi-satellite motion for about a century and will remain so for several more centuries. It's the most stable known quasi-satellite of Earth, maintaining the relationship much longer than typical. Another is 2023 FW13, discovered in 2023. This one has a more complex relationship, transitioning between quasi-satellite motion and horseshoe orbits. Its behavior demonstrates how these dynamical states can shift over time. Kamo-Oalewa, officially 2016 HO3, mentioned earlier, became particularly interesting when spectroscopic observations suggested its composition might resemble lunar material. This sparked speculation that it could be a fragment ejected from the Moon by an ancient impact. If true, it would be Earth material that escaped, orbited the Sun independently, then returned to become a quasi-satellite. That hypothesis remains unconfirmed, but demonstrates the scientific interest these objects generate. Each quasi-satellite provides opportunities to study near-Earth orbital dynamics. They exist in parameter space between fully captured satellites and independent asteroids. Understanding how they form, how long they persist, and what causes them to transition between different states improves our models of gravitational interactions throughout the solar system. 2025 PN7's proximity to Earth makes it an intriguing target for potential spacecraft missions. Its quasi-satellite orbit means it remains relatively close in dynamical terms, even though absolute distances vary. Reaching the asteroid wouldn't require the enormous delta V needed to travel to the main asteroid belt. It's already near Earth's orbit. A spacecraft could potentially rendezvous with relatively modest propulsion requirements compared to missions targeting distant bodies. Sample return missions are particularly attractive. Landing on a small asteroid, collecting samples, and returning them to Earth would provide pristine material for laboratory analysis. If 2025 PN7 is a captured interstellar object, which is possible though unlikely, those samples would be invaluable. Even if it's a standard near-Earth asteroid, studying its composition adds to our understanding of these objects. The asteroid's small size poses challenges. Low gravity means landing and anchoring are difficult. Spacecraft might need to use harpoons, drills, or other mechanisms to secure themselves. But missions like Hayabusa 2 and OSIRIS-REx have demonstrated that sampling small asteroids is achievable with current technology. Timing matters for any mission. The asteroid's orbit relative to Earth varies. Some years offer better launch windows than others. Mission planners would need to optimize trajectory design to minimize fuel requirements and flight time. No missions to 2025 PN7 are currently funded or scheduled. But the asteroid joins a list of interesting near-Earth objects that could be visited if resources and priorities align. Its quasi-satellite status makes it scientifically interesting beyond just being another small asteroid. Studying quasi-satellites like 2025 PN7 provides insights that extend beyond individual objects. These systems test our understanding of orbital mechanics in complex gravitational environments. The solar system is full of orbital resonances. Jupiter's moons show them. Saturn's rings are sculpted by them. Near-Earth space contains them in forms like quasi-satellites and horseshoe orbits. Each example helps refine theoretical models and computational simulations of how gravity works when multiple bodies interact. Quasi-satellites also constrain models of how planets capture satellites. The Moon is captured, though probably through a giant impact rather than gravitational capture of a passing body. But smaller moons around other planets might have been captured gravitationally. Understanding the dynamical conditions that allow temporary relationships like quasi-satellites helps understand what conditions allow permanent capture. Long-term orbital evolution is another area where quasi-satellites provide data. Predicting how objects move over millions of years is challenging. Perturbations accumulate. Chaos can emerge. Quasi-satellites, with their finite durations and predictable transitions, offer cases where models can be tested against observations over humanly observable timescales. The discoveries also have practical implications. As space becomes more crowded with satellites and debris, understanding natural orbital dynamics helps predict where objects will be. Quasi-satellites follow specific patterns. Recognizing those patterns prevents misidentifying them as artificial objects or threats. So does Earth actually have two moons? The answer depends on definitions. If moon means a natural satellite gravitationally bound to orbit the planet, then no. 2025 PN7 orbits the Sun, not Earth. It's not captured. It's not gravitationally dominated by Earth. It's an independent body that happens to share Earth's solar orbit in synchronized fashion. If moon means any natural companion that moves through space with Earth for extended periods, then yes, temporarily. 2025 PN7 will accompany Earth for decades, moving in lockstep around the Sun, maintaining proximity that makes it a companion even without gravitational capture. The terminology matters less than the dynamics. Regardless of what we call it, 2025 PN7 demonstrates that Earth's dynamical environment extends beyond just the captured moon. Small bodies can become temporary companions through resonant orbital configurations that don't require capture. This isn't unique to Earth. Other planets have quasi-satellites too. Mars has several. Jupiter's Trojan asteroids, while not quasi-satellites, show similar resonant dynamics. Throughout the solar system, planets influence nearby small bodies in ways that create temporary relationships without permanent capture. 2025 PN7 is a natural phenomenon emerging from gravitational dynamics. No special event caused it. No unusual circumstance created it. It's simply what happens when a small asteroid happens to have an orbit nearly identical to Earth's. Orbital mechanics do the rest, creating the synchronized motion we observe. As I record this, 2025 PN7 continues its journey around the Sun, maintaining its quasi-satellite relationship with Earth. For the next several decades, it will be our cosmic companion, looping through space in patterns that appear Earth-centered but result from independent solar orbits synchronized by fortunate dynamical coincidence. This isn't Earth's first quasi-satellite and won't be the last. These temporary companions come and go as orbital evolution brings small asteroids into and out of the right configurations. Each one is an opportunity to study near-Earth dynamics, to test orbital models, to understand how planets and small bodies interact gravitationally. Does Earth have two moons? Not by the strict definition that requires gravitational capture, but for the next half-century, we do have a second natural companion, a small asteroid traveling with us through space, a reminder that our planetary neighborhood is more dynamically complex than simple models suggest. The solar system is never static. Orbits evolve. Objects transition between different dynamical states. Temporary relationships form and dissolve over decades and centuries. 2025 PN7 is one example of this ongoing evolution, captured during a brief window when it shares Earth's journey. Scientists will continue tracking this object, refining orbital predictions, monitoring how the quasi-satellite relationship evolves. Observations over coming years will test models and might reveal surprises. Perhaps the relationship will last longer than predicted, perhaps shorter, perhaps transitions will occur that weren't anticipated. And somewhere in that data, in the precise measurements of position and motion, lessons will emerge about how gravity sculpts trajectories and creates the beautiful complexity we observe when we look carefully at the space around our planet. Earth's temporary second moon reminds us that even in our own neighborhood, space continues revealing surprises. That the dynamics governing motion are rich and subtle, that nature creates relationships between objects that seem almost designed but emerge purely from gravitational physics operating over time. Comment below. Would you want to see a mission visit 2025 PN7? And subscribe, because this quasi-satellite will be observable for decades. And as scientists continue tracking its motion and refining our understanding of Earth's dynamic environment, we'll bring you updates on this cosmic companion, sharing our journey around the Sunday.